All right, welcome to part 2 of Tuesday's lecture. So we're going to continue with examples of angular momentum. So once again, we're going to look at, we looked at a teeter-totter before, so now we're going to look at a merry-go-round. This is the chapter where we get to do all of the examples involving playground equipment because, we're all kids at heart. All right, so once again, I'm going to use one of my favorite people for the example, my daughter Esther. So Esther jumps onto the merry-go-round at Windmill Park. This clearly took place before all the parks got closed. And when she does this, the merry-go-round goes from at rest to spinning. The question is, at what rate? We don't know anything about how many revolutions it's making per minute or how many radians it's covering per second. Okay, so basically what we have, here's Esther, fountain of endless energy, and a very long torso apparently, running towards a circle which has been distorted of radius r, mass m. She runs towards it with a straight line, and she's going to jump here. She's got tangential velocity, and her mass is little m. So she runs at it in a straight line, jumps, and then, of course, if you do that, the merry-go-round will start to spin. If you don't believe me, you can, after they open up parks in your area, feel free to take a running jump carefully so that you do not get hurt onto a merry-go-round, and you will see this happen. Or perhaps you have memories of childhood of doing just this. All right. So to describe this situation, both the momentum principle and the energy principle are insufficient. We really need the angular momentum principle. I mean, we could get her from here to here using momentum principle, but then she's at rest on the merry-go-round, but clearly is still moving, so momentum principle isn't going to cut it. And energy principle gives us basically nothing. Kinetic energy? Okay, so for this we need the angular momentum principle. And I told you before, you can attribute angular momentum to running in a straight line. We're going to see this here. So Esther does have angular momentum when she is running at this straight line with respect to the axle on the merry-go-round. Remember, we only know, all we need is r, the distance or the vector between the object and the point of interest, and we need momentum, which we can have even from something that's going in a straight line path. What happens next? Certainly a physics problem doesn't take away from the angular momentum at that moment. So straight line, angular momentum will now come into play. All right, so the mass of the merry-go-round is about, by the way, I made these numbers up. I don't know how massive that merry-go-round at Windmill Park is. We're also going to assume it's nearly frictionless. I can assure you that assumption is going to be a stretch. The radius is about 1.2 meters. We're going to assume low friction axle, which is a big stretch. But hey, we'll work with it. Okay, so that is the merry-go-round. Esther is 5 meters away, and her mass is 17 kilograms, and her velocity is about 1.5 meters per second. The question is, how fast does the disk rotate after collision? Okay, so let's look at the setup. Our system is the disk plus Esther. The surroundings. So Esther starts out, is 5 meters away. Oh, oops, okay. I thought that looked strange. Let me try that again. The surroundings are Earth, the ground, and the axle. So these are not within the system. They can all bring some force. They can all do some work. All right, so the initial state, here we go. Esther is 5 meters away, and her velocity is 1.5 meters per second. And the final state, just after collision. Esther is riding the merry-go-round. Now, in real life, my daughter is actually quite a cautious child, and she would never do this, or at least not presently. We'll see if she gets she gets a little bit gutsier as she gets older. But right now, she's just very cautious, and that's okay. All right, so let's draw some more diagrams. So we said this was 1.2 meters. We have axle, which is going to be our point that we're going to be looking at in terms of angular momentum. The axle has a force on the system. This is 5 meters. This is where she starts. And we've got velocity of 1.5 meters per second. And if we recall, this mass is equal to 400 kilograms, and Esther's mass is 17 kilograms. All right, so what we're going to be interested in is the force from the axle at the time of impact. It will change the momentum of the system. Okay, so here is what we are analyzing. And so as I said before, by the way, especially on your final exam, make sure you write out which principle you're using, because you're going to have energy principle problems, angular momentum principle problems, and momentum principle problems all on the same exam. So help me keep your work straight, and also for your own sake, keep your work straight. Okay, so the final angular momentum must be equal to the initial angular momentum plus the net torque over the length of time that torque was applied. So we can choose RA, which we've kind of already done. We choose the easiest A, and make it the axle. So always think when you're setting up a problem, what is going to be the easiest choice? All right, so we have 0 torque. There's really nothing providing a twist. So Esther's going to collide into the merry-go-round, but that's different than a torque. So we have a net torque of 0, which is the type of problems that we're doing. And this comes from our choice of the center A being the point that we're looking at relative to. If you chose a different point, you would have torque. So just something to keep in mind. All right, so now we can say that final angular momentum must equal initial angular momentum. There's nothing giving it any torque. So the interaction takes place. Please read your problems very carefully about what planes they're in. This one takes place in the xz plane. So the angular momentum will be in y. So, okay. So we can go ahead, draw another picture. You can never really have too many pictures. Here's our point A. $1.2 meters, 5 meters, and RA is right here. Let me put a different color on that. All right, so RA is going to be the direct line from A to the point where she's starting 5 meters away. And so have an angle theta. Okay, so initial angular momentum comes only from Esther. The merry-go-round is not spinning. So one way, if you know what a couple different ways you can go after angular momentum. So you could take the magnitude of the two vectors and find the sine, you could find the angle between them and take the sine of that. So I tend to prefer to use cross products whenever I can over magnitudes and sine and cosine functions. This is just my personal preference. But you know, I try to do problems using a variety of different techniques, with the idea being that I want to show you that there's lots of right ways to do this. The question is, what makes the most sense to you? So in the case of looking, so we know it's just going to be in the y component. In that case, we know that we're looking at z p x minus x p z. So that if we look at our cross product formulation, that we have the components here that are going to make that up. So you could also think of it, if you like to think of it in terms of your r vector being r sub z, or r sub x, r sub y, r sub z, instead of x, y, z, then you could also write this r sub z px minus r sub x pz. Same thing. Okay, so we know that the momentum in Z is equal to 0. So this component here goes to 0. So then all we really have is ZPX. Okay, so that's 1.2 meters times 17 kilograms times 1.5 meters per second. So let me just draw a couple things. This is your Z, this is your X. So 1.2 meters times 17 kilograms times 1.5 meters per second. And you get that the angular momentum in Y using this particular technique is equal to 30.6 kilogram meters per second. On your own, do another method. Play around, see which ones make the most sense to you. Maybe it's this way, maybe it's something else. And really, I have found this to be very, very person dependent. No one is better or worse for preferring one method over another. Okay, so now we go after final angular momentum. And this is going to have spin or rotational angular momentum. And translational. Angular momentum. And this is going to be related to Esther being on the ride. Okay, so it has angular speed omega, and Esther's speed is omega r, which is equal to omega 1.2 meters. Let's make that a capital R. Okay, so we have speed omega times 1.2 meters. We know that angular momentum y final must be equal to angular momentum y initial, which is equal to 30.6 kilogram meters per second. Angular momentum y initial is equal to the moment of inertia times omega plus rmv. Again, we're splitting out the two components of angular momentum. So this is equal to 1/2 mr squared omega plus rm omega r. Plugging this in here. This is equal to 1/2. The mass of the merry-go-round is 400 kilograms times 1.2 squared meters for the radius times omega plus 17 kilograms times 1.2 meters quantity squared times omega. And so we have 30.6 kilogram meters per second is equal to omega times 1/2 times 400 times 1.2 squared plus 17 times 1.2 quantity squared. This is of course kilograms, meters, kilograms, meters. All right, so what we have is 30.6 kilogram meters per second is equal to omega times 312.48 kilogram meters squared, and therefore omega is equal to 0.0979 radians per second. And there you have it. So all we did was use the conservation of angular momentum and everything that we learned about the momentum formulations to go after this angular speed. So, and I'm just going to note that prior to the collision, linear angular momentum all came from Esther. And her speed after collision is omega r, which is equal to 0.117 meters per second. And if we were to think about this in terms of the energy principle, you would have an inelastic collision where your kinetic energy decreases and internal energy increases. And as a result, Esther and the merry-go-round would get warmer. All right, so thus ends that example. So moving on to frictional torque. So we know from experience, friction is something we have to contend with. So, and axles can introduce friction. And so frictional torque so R cross F about the center of the axle. So if you've ever had like a squeaky wheel, you're dealing with frictional torque. So your axle is introducing some friction. And so they're basically the guidelines for whether or not you can neglect frictional torque are as follows. So here are the guidelines. So here are the guidelines for safely neglecting frictional torque. Otherwise, you need to use R cross F, which is the coefficient or the frictional force. So the coefficient of friction is small. So you put some WD-40 on that, and you're good. Or axle to inside surface is small. So R is small, therefore R cross F is small. By the way, in real life, a small axle is not always practical. There's other implications of having a small axle. It will decrease your the impact of friction, but it can be harder to torque. Okay, so, and in a rotational collision, you can safely neglect friction if delta t is too small for any measurable tau delta t. So these are the rules for safely neglecting frictional torque. Coefficient of friction is small, axle to inside of surface is small, therefore making R cross F small, or you're dealing with a collision, and in which case you can play by normal collision rules. All right, we will stop part 2 of Tuesday's lecture here. I will see you for Wednesday's lecture.